Hello, and welcome to another 2-minute tip. Today we're going to go over the basic use, what it is, and why you would want to use a phantom. This is one of the most basic phantoms that you'll find. There's a wide variety of phantoms used for ultrasound, and in general a phantom just means it's something that's taken place of a body that you can image. The real advantages of that is it gives you something that's consistent and stable, that you're looking at the same thing each time. When you make photographs of a phantom image on a particular ultrasound machine with a particular transducer, you can then use that as a reference photo to go back over time and look and find out if the image has changed, if the photography has changed, or in fact if there's problems with the system that were not there previously. And that's one of the main features, is actually to document it. The phantom is used primarily for Q&A and assisting in troubleshooting with the ultrasound image or a probe issue. It provides constant and reproducible images of known targets and distances, and it allows you to document the system performance over time. The phantom itself physically is made up of a variety of items. The most common is one that's similar to this. It's made of something like a ballistic gel. It looks like a large rubber block. And the second most common phantom is probably the tissue equivalency phantom, that is actually filled inside with a gelatin type material that, if you cut it open and look, has the appearance of being filled with graphite particles, so that it actually mimics the appearance of a liver when you're doing an exam on it. All phantom has to transmit the ultrasound signal at the same velocity as it does through the body in order to make measurements correct and have the image correct. And also it has to have the same amount of attenuation as the body, meaning as the ultrasound signal goes in, it's attenuated and it loses signal as it goes down and bounces back up again, and it has to lose that signal at roughly the same rate as it does in the body. This phantom, you can see, it's got a diagram, like all of them do on the outside, showing you what's inside the phantom. Here you'll see a series of rods that are going from light to dark, and they appear as circles on here. In fact, that's actually a plexiglass rod going sideways through the image this direction. And I'll be able to show you that to you when we're scanning. Over here, this is the same thing, only these rods are all clear. These vary in their density. Over on this side, what looks like pins as you scan the image are actually, again, wires, very thin 1mm wires, typically going through the system this way. When you scan in the plane this direction, what you get is an image that looks just like this. And these items are all put on here to do something different. We're going to scan and see each one of these in a moment, but I'm just going to describe what we have on here. The primary functions of the phantom are to show axial and lateral resolution. So it wants to show how good your resolution is, going in the direction of the beam, and also sideways. This type of wire marker display is particularly good for that. The wires get progressively closer as they come down and curve and turn from axial to lateral. And you'll look at the image and we'll see how closely these wires can be and still be seen as a separate and distinct echo on the monitor. That's what the goal is for checking the axial and lateral resolution. In addition to that, we're going to check both the axial and the lateral measurements. When you go to make a measurement, whether it's to look at the size of a particular gland, to see the size of an occlusion, or anything else, you want to know that that measurement's accurate. So there's wire markers at fixed distances in here, and they're labeled on here. We can go in, we'll actually make a measurement with the system and see if it matches up to that. Contrast resolution is what you can see right over here. It wants to find out how well you can see changes in density, not just a change of a size of an object. There's only 6 steps across here, but you can actually watch it go from being able to transmit all the echoes through it, it'll be perfectly clear, to passing the echoes and not being able to see those on the bottom. And you want to be able to see that you've got nice gradation through here. These are the same size. These represent cyst, and these are hollow plexiglass rods again, and they're clear as you look at them with the ultrasound. So what you're trying to do is find out how small of an object. You can still see the difference in the contrast between the surrounding tissue and, say, a cyst, and you also want to make sure that that cyst is clear. It doesn't have a lot of echoes in it. And that's what each one of these are for. You also have another set that shows you near the near field, so you can take a look at a high frequency probe and see how well it's seeing in the near field, and if it can see down to the 1 centimeter marker. In a lot of cases with a transducer that's somewhat obliterated, and you'd use something like a standoff pad to see better there. That's what this is for, to evaluate your image and document it. And now let me show you what each one of these look like on the monitor. Put the transducer on top of the phantom. Have it covered with gel to make good contact. And you'll see a representation on the monitor, very similar to what you're looking at here. You'll see that these are actually very small 1mm pins or wires going across there. And when you look at your resolution, you're looking for axial resolution along the axis of the plane and lateral resolution. And what you can see is that the axial resolution is quite good. Very small in this direction. Lateral resolution is not so good. It's spreading out. That's just a function of the type of transducer I have here. I have a high frequency curved array transducer. The curved array spreads out farther, just like the spokes of a bicycle, and you'll get worse resolution on there. If I have a high frequency linear transducer, you'll see something very, very much like you're looking at here. Very distinct pinpoints. And this is what you're looking at. That's not good or bad. It's a function of the system and transducer combination, as well as things like focus and depth. What you would do is take a photograph of this, and over time you'd be able to tell if that image is staying the same, if you're losing resolution in one direction or the other, or even if you had dropout along the area somewhere. That's for axial and lateral resolution. For axial and lateral measurements, we'll do right here. Let me freeze. Looking at the lines down here are matching up the lines coming down here. They're 1 centimeter apart, and they start at a fixed surface fixed distance from the surface. That changes a little bit as you push up and down here. That'll move. So typically what you'll want to do is not measure from the surface, but measure between a series of dots on here.